Hi everyone, my name is Omkar Deshpande. I am the head of curriculum at IK. In these videos, I am going to go through some advanced algorithms on graphs. I am assuming that you have gone through the pre-class videos and the live class, and so I don't have to remind you about anything that was covered in the pre-class videos and the live class. I'll just assume that you're already familiar with it as I cover this new and more advanced material. So let's begin by going back to a problem that should hopefully look very familiar by now, calculating the number of connected components in an undirected graph. So in the first set of videos here, I'm going to be focused exclusively on undirected graphs. And this was one of the problems that I covered in both my pre-class videos and the live class. You might remember, for example, that we were given as input an undirected graph by specifying the number of vertices. For example, if n, the number of vertices, is equal to 5, we are supposed to interpret it as there being 5 vertices with IDs from 0 to 5 minus 1. We are assuming a convenient range of vertex IDs from 0 to n minus 1 in general. And we will also assume that we are given an edge list listing out the edges in no particular order. So for example, in this graph, since there are 5 vertices, I could just draw them out like this, and this first edge between 0 and 1 gets shown as an undirected line like this. This edge from 1 to 2 gets shown like that. This edge from 3 to 4 gets shown like that. And so by visual inspection, you can see that this graph, this undirected graph, has 2 connected components. The way we solved this in the live class was by going through a 3-step process. In the first step, we actually build the graph, by which I mean we build the adjacency list or the adjacency map of the graph from the given input, from the input edge list. And once we do that, then in the second step, we either follow breadth first search or depth first search to explore the whole graph. So we launch breadth first search, for example, from say vertex 0, and then we explore all the vertices that are reachable from vertex 0, marking them as visited. And once our BFS terminates, then we check if there are any other vertices which we have not yet touched during our exploration, and if so, then we launch multiple BFS or DFS calls as required until every single vertex of the graph has been explored. So we also had an outer loop which went through each vertex one by one, checking if it was visited or not, and if it was not visited, launching a new BFS or DFS call with that unvisited vertex as the source. And the number of such BFS or DFS calls that had to be launched basically gave us the number of connected components in the undirected graph. So this is something you should be able to recall if you have gone through the pre-class videos and the live class. What I will do now is to slightly change the context in the problem. What if the edges in this graph were not given to us in one shot, but they were coming in dynamically? So at the beginning, we have not seen any edge, and we know that there are 5 vertices in the graph. So as far as we are concerned, those 5 vertices can be drawn like this without any edge between them. And then some time passes and we see the first edge between 0 and 1. So before we saw that edge, the number of connected components in at the very beginning was 5. But suppose this new edge comes in, linking 0 and 1 together. How many connected components do we have now? Well, we have 4 connected components. Then we see the next edge, It comes in after some time, linking 1 and 2 together. How many connected components do we have now? Well, we have 3 connected components. Then another edge comes in, linking 3 and 4 together, and that makes our connected components 2 in number. So our connected components are coming down. They started from 5, then they came down to 4, then to 3, then to 2, and if there is an edge from 2 to 3, that number will come down to 1, after which any more edges will not affect that number. So the question is, can we output the number of connected components after every edge comes in? So we are not looking for a one-time answer at the end once all the edges have come in. We are asking for an answer on a per edge basis. This is sort of similar to what we saw in sorting. If you remember, in sorting we had this problem of finding the kth largest element in an unsorted array, and in that problem all the elements of the array were given to you in advance, and we saw that quick select was the best solution in that context. And then we changed the context of the problem. We said, what if the numbers in the unsorted array were not given in one shot, but they were coming in one at a time? In that case, you might remember that the best solution was not quick select, but to use a min heap or a max heap, depending on whether it was the kth largest or the kth smallest problem. So we are asking something similar here. What if the edges were not given in one shot, but they were coming in one at a time, almost like in a streaming context? How do we calculate and update the number of connected components dynamically so that we can keep spitting out that number after seeing every edge? Well, a naive approach would be to repeat this 3-step process after seeing every edge. So every time a new edge comes in, we add it to the adjacency list for the graph, and then we run the outer loop to launch BFS or DFS as many times as needed to explore the whole graph. And we just keep a count of how many times we had to launch BFS or DFS, and that counter will give us the number of connected components at each step. How much time would this naive approach take? The naive approach, which uses BFS or DFS, would require order m plus n time each time that we follow this 3-step process. And since we are doing that for every edge that comes in, we would effectively be taking time proportional to order m plus n multiplied by m. So this would be order of mn plus m square. So if the graph is dense, which means the number of edges is order of n square, or nearly quadratic in n, then this mn plus m square is going to be dominated by the m square term. So this is going to become order m square if the graph is dense. If the graph is sparse, however, which means that the number of edges is order of n, and this is by far the most frequent scenario, we are going to be generally assuming that our graphs are sparse. In that case, our running time, well, here the running time should be a function of m. Here our running time t of n is going to be equal to mn plus m square, but since m is order n, I can write t of n as equal to order n square. So it's still quadratic in the number of vertices, and you might recall from the pre-class videos on sorting that if you have a quadratic time algorithm, then in the worst case, assuming the worst case is quadratic time, we would be able to run that kind of algorithm on inputs that are at most of size say a few tens of thousands. Beyond that, the amount of time that we need for the algorithm to terminate starts looking unreasonable. And so this kind of naive approach will not be able to run on graphs that have more than a few tens of thousands of vertices and a proportionate number of edges. So we want to do better than this, but the question is how?
Want to become a software engineer at Google? You can, like thousands of our students. You just need to learn from those who've already cleared FANG interviews. At Interview Kickstart, our interview prep courses are developed and taught live by 150 plus instructors from Tier 1 companies like Google and Facebook. Our courses are tailored to help you crack software engineering domain interviews, including back-end, full stack, machine learning, embedded systems, data science, and more. To learn more, book your free webinar slot today